All right, everybody. So let's get started on reviewing the Robinson annulation. So let's talk a little bit about what is going on here in the Robinson annulation. We went over some practice in class, so we did some problems, and we'll continue doing some problems in class, but I wanted to kind of talk about the reasons why we may want to do some things, and then we'll go through how to do it. All right, so the Robinson annulation, remember, is two steps. The Michael addition, which we've done and practiced in class, and you had your videos on that, and then the aldol condensation, and you're going to get your product from the Michael addition attacking the molecule itself and closing up in a ring, and that's why we call it annulation, because one meaning of annulation is to close inside of a ring. So we are going to draw this, and we're going to practice this. So we're going to do a practice problem, and we did one in class, and we're going to continue doing practice, like I said. But what I want to emphasize in this lecture is that we need to use weaker nucleophiles for the Michael addition, like enamines, like Gilman's, or we might use doubly stabilized carbonyls. And we can use these to attack the beta position. So remember, in class, we practiced some problems, and in our previous lecture we talked about this, that we use these weaker nucleophiles because the stronger ones are going to attack the carbonyl itself rather than the beta position on the alpha-beta unsaturated carbonyl. So we're going to go through the mechanism again, but let's talk a little bit about some applications of these. So we've been talking about applications in class many times. We have our molecule of the week every week. Sometimes we have our green chemistry application. So let's talk a little bit about some of these. One application for this is that we can make a lot of these molecules that are multiple rings, and as you can see in some of the applications that we've talked about so far, a lot of them had rings, and a lot of molecules in nature have rings. A lot of pharmaceuticals have rings. If we talk about new materials for plastics and things like that, a lot of our polymers are in rings, and so it's very important that we learn how to effectively make a ring. Another application of the Robinson annulation is the atom economy. Since we're primarily, unless we add something to the mechanism, since we're primarily using the same atoms to attack each other, our atom economy is fairly high. Now, here is where it could lower because of the choice of our starting material. So for example, if we start with a ketone, not a double ketone like a dione, but if we had something that would be like a cyclohexanone, well then it is going to need to be converted to something weaker like an enamine. And if we convert to an enamine, now we're adding another step. Now it's not that bad because the enamines are fairly easy and fairly simple, but it is something that's going to add what we call add auxiliaries, or add extra protection groups, or add extra materials into our reaction that also lowers our atom economy. It will also lower yield. For every reaction you do, it lowers the yield. So let's jump back into going over the mechanism. Let's draw the mechanism, but what I want to do is focus on something that we practiced in class, but I want to revisit, is that when we do the Robinson annulation, we want to use these weaker nucleophiles to attack at the beta position on the alpha-beta unsaturated carbonyls. And if we just use a regular ketone, we're going to end up with a side reaction where if we deprotonate at the alpha position, now we've formed a nucleophile that then can just do an aldol condensation with itself or with another carbonyl. So let us therefore do a conversion with this, so we can do a reaction that we've practiced already and you saw in your videos. We can do a reaction with a amine And so we can convert this to an enamine. So to make an enamine, remember we want a secondary amine. And in that mechanism, we also need catalytic acid. So let's go ahead and draw this mechanism. So first, what I'm doing is making an enamine. And our enamine will help us to make a weaker carbonyl. So I'm putting carbonyl in brackets because it's not a carbonyl, but it's essentially masking a carbonyl. And remember, there could be multiple ways in which we do this mechanism. So I'm going to draw it one way, but we've talked about a couple of different steps that are also likely and possible. So one way that you guys may draw it, it's not going to happen just because of orbital overlap. Not going to happen as often, but in mechanistically, it's not incorrect. It's just orbital overlap wise, having your intramolecular proton transfer can still work, but I'm going to do it a little bit the longer way, which might be a little bit more comfortable for some students. So I'm going to shuffle this proton around. And remember, these are equilibrium steps, which is very important for us because we're going to reverse them later on. So we deprotonate this nitrogen because we want to make that nitrogen stay, but we're going to protonate. We're going to take that hydrogen. So again, we just kind of shuffled it around. We just made H3O+. Kind of just shuffled it around. And made our H3O+, which is our acid, to protonate. All right, so why are we doing that? So we're doing this so that we'll eventually make that oxygen a leaving group, but it's not going to leave negative. It's not even going to leave while it's an OH. It's going to leave when you protonate it again. So remember, this is a catalytic solution, so we will still have some acid. It's a little bit acidic in that flask, usually around a pH of 3 to 5. Let's draw in our lone pairs. Okay. And a couple of reminders, please don't use the negative charges to attack because they're not attacking anything. It's the lone pairs that are attacking. And don't point arrows towards plus charges because the plus charges are imaginary things, okay? Now we have a very good leaving group, and you can draw this one of two ways. You can either draw the enamine, the nitrogen kicking out the leaving group, or if you wanted to, you could go ahead and draw this where the water leaves first and then the leaving group, the nitrogen comes in. Either which way, again, there's an overlap issue with orbitals that might affect which one happens more likely, but mechanistically, we are okay if you drew it that way. So we're going to get our iminium ion, which will then later on we'll be able to convert it back to the carbonyl because we're going to reverse all these steps, so the water will come back in and do all of that. Now what's going to happen is if we were to draw the resonance structure, we'll see that this carbon is positive. And because of that, we can have an elimination. So any extra nitrogen we have, because as we now know, nitrogens are pretty decent bases, especially when they're alkylated, as this one is. We're going to end up with an elimination, and we get our enamine. Now, I'm just using R for now, but you might have ethyls, methyls, propyls, whatever it is. So just be aware of that whenever you have to draw these mechanisms. And again, they're all equilibrium steps. So if I skip an equilibrium arrow, it's not intentional. Now, when we do the Michael addition, we are going to attack at the beta position of my carbonyl, and we're going to attack from the weak Michael donor that we have. So this Michael donor, this carbon has a full octet, so it has to break. What I'm going to do is go ahead and label things with numbers, because I'm going to describe them that way, especially when we're joining. I would strongly recommend adding numbers to things to help us when we draw our mechanisms. So this will come over, come up, we break that pi bond. Now I'm also going to label this 7 and 6. So carbon 7 here, carbon 6. 6 is going to be now attached to carbon number 2. Carbon 2 is attached to 3. We move that pi bond between 3 and 4. So there's a pi bond there. We also had our carbonyl open up on carbon 4. So this was carbon 5, and we are missing carbon number 1, so this is carbon number 1. Now, our next thing that's going to happen is that we are going to protonate and then tautomerize. And we can draw our tautomerization a couple of different ways. So we can draw the resonance form of this to stabilize this, to make it the iminium ion back again, or we can leave it the way that it is for the next step, either which one that you want to do. This one is a little bit more stable because everybody has all its octet. So let's redraw everybody. So one thing that has to happen here, one of our last steps, is a protonation step. So we have acid in this reaction. So this ends up being protonated, and now we can do our tautomerization. We can either do an intramolecular tautomerization if you want, if that's more comfortable to you, or we can shuffle around our hydrogen. So in class we've done it the intramolecular way. I'm going to draw it the other way, because again, a lot of these can be done different ways, and you can choose whatever is more comfortable for you. And then I'm going to take care of the iminium ion in a bit, but I usually do it all in one step, but I'm going to come back and show you the other side after I've done this part. So if I pick up a hydrogen, the hydrogen is going to go to carbon 3. And then we can easily deprotonate this. Now I'm going to take care of the iminium side because both things are going to happen in our reaction. You can draw them out separately, but from a mechanistic standpoint, it's okay if you draw them out together. So we've drawn this before. Water can come in, open the iminium ion up. Because what we want to do now is replace the iminium ion with OH so that we can eventually form our carbonyl. All right. So, like I said, I'm going to kind of go back and forth, and you can draw them separately, but just for time's sake and space sake, I'm going to draw them all kind of at the same time on both sides of our molecule. So we need to get rid of the hydrogen on our water, because otherwise it's just going to go backwards and leave. So to prevent it from going backwards, what I'm going to do is take another molecule of water, or we can take our amine if there's any left over, but more than likely it's water. Deprotonate. And then, and you notice that I'm talking through it, not just for your own sake, for learning purposes. I'm talking through it because it kind of helps me follow along. I strongly recommend, as I've told you guys multiple times in class, multiple times in videos, you're not crazy. It's okay to talk to yourself while you're doing mechanisms. Just don't talk out loud in the test, that's all. But you can talk yourself through it. You can even write notes. That will help you. But the more you practice, the better you'll get at this. So I want the nitrogen to leave. So I need to protonate it. So I'm going to go ahead and I'm going to protonate the nitrogen to get it to leave. Remember, what we do in these mechanisms, many things can happen, but the thing that ideally we are going to draw, so we're not drawing everything, but we're drawing the parts that lead us to the product. So other things happen, like the hydrogens go back on the oxygen, but that never leads us to our product. And so in that case, that just reverses the equilibrium. And in that case, we just end up where we were to begin with, and it will just keep going forward until we eventually go all the way forward. Okay, now the nitrogen is a decent leaving group, so it can leave. Now you can do this in one step or in 2 steps like I did here. It's up to you. Mechanistically, it's not wrong. Orbital-wise, it might not be so right, but I'm only really concerned about your mechanism right now. All right, so our last step then has to be deprotonation. Now we're going to do the aldol condensation. So when you look at these problems, when you see me draw them, the next step is that we take base to our solution, and I'm going to number everything again so that we can follow along. 1, 2, 3, 4, 5. And then I had numbered this 7 and 6. We're going to do an aldol condensation, but remember, the aim is for the more stable ring. So whatever hydrogen you remove to do this process, we want to have the most stable ring. So if I were to do this, remember there are lots of different alpha positions, and remove the hydrogen here, that means the ring size that I'm going to form is 1, 2, 3, 4. That's not going to happen to close that ring up. But I could potentially, this is a very easy hydrogen, and we have one other hydrogen that we could try, but this is an easy one to deprotonate. And now we can do our aldol. And remember, the driving force, which is the question that keeps coming up over and over, the driving force for this aldol is not going to be the aldol product, but the aldol condensation product. And we did some calculations when we did this. And remember, you can do it under acid or you can do it under base. I'm doing it in this case under basic conditions. But our calculations showed us from our Spartan that the conjugated species is the most stable. Now, before I keep drawing, I'm going to number again. 7, 6, 1, 2, 3. Sorry. I'm going to renumber. And what I want to do is number, because I'm going to show you how I would draw this, because that's always a common question. Like, how do you begin drawing it? It's easier for me to draw the rings first and then to do the process of filling in everything, and that's why I like to number things. So I'm going to be attaching 5 to 7, and it's going to give me a 1, 2, 3, 4, 5, 6-membered ring. So that means this side of my cyclohexane should have a 6-membered ring attached. So if this is 7 and 6, that means my alkoxide that I formed. Remember, these acyl nucleophilic additions form the tetrahedral alkoxide intermediate. Number 5 is joining to number 7, so that's number 5. Then number 4 is attached to number 5. Number 4 had my carbonyl. Then number 3, and then number 2 had number 1 attached to it. So our next step, we're going to protonate our alkoxide, and again, this is not a very favorable, it works, it's not, the equilibrium is not extremely favorable, but again, what drives our process is what's going to happen next. So we're going to do an elimination. So it's an E, basically like an E2 that we learned in the first semester. And the driving force, because OHs are not good leaving groups, is that alpha beta unsaturated carbonyl. Now I can do all sorts of other things with this alpha beta unsaturated carbonyl as we learned before, but that's kind of what's going on. All right.
All right, so let's try this problem here, 22.8, and I just had my pen. Now I don't remember where I put it. All right, so when we do this, the question is asking us to figure out what the molecule here is. So we can first do the HDI. So that's 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of plus the number of nitrogens divided by 2. And so when we do that, it's 2 times 6 plus 2 minus 15 plus 1 over 2. So that's 12 plus 2 minus 15 plus 1. It's 14 minus 15 plus 1. And so that's 0. So there's no pi bonds and there's no rings. And you only have 2 peaks on the NMR, so both the carbon and the proton. This one is a integrates for 3, and it's a triplet, but notice that there's 15 hydrogens. So because there's 15 and there's only 5 shown here, whatever is here could be repeated 3 times to give you that. And it would make sense because if there's only 2 sets of hydrogens, that means the rest need to be basically the same type of thing, and the same with the carbon. So what we can figure is whatever the structure is, these hydrogens are closer to the nitrogen, this carbon is closer to the nitrogen, and because we have no double bonds, we know this is a triplet, so that means it has 2 neighbors. And because it integrates for 3, we can imagine that it's probably a CH3 next to a CH2. And over here, I have a quartet, which means that I have 3 neighbors. And it integrates for 2, which makes sense. So this would be A, this would be B, so this could be A and B. And this is attached to nitrogen. So what does that mean? It's more than likely that it's triethylamine, where everything is identical, and we see the same thing on the carbon NMR. This peak would represent the carbon A. This one would represent B, just because there must be some sort of symmetry. Otherwise, there would be no reason why you would only get 2 peaks if there's 6 carbons on the structure. So there must be some sort of symmetry on the structure. So our next problem that we're going to do, I'm going to clear the screen, and I'm going to go to problem 22.5. in your textbook. Okay, so this problem asks you to draw the Gabriel mechanism for the last step. I'm just going to draw the kind of the initiation to get to this point. So if you were given this molecule under basic conditions, usually you use potassium hydroxide. You get the negative charge on the nitrogen, and so I'm just showing you how we ended up with this because that's, even though that's not what the question was asking. So we can take this molecule, react it with an alkyl halide, to give you this, so something R with the leaving group on there. And then to get this reaction, what they're asking for is you would need the hydroxide. So this goes back to our previous chapter. This would attack here and open this pi bond up. Making our alkoxide with our oxygen on there and our nitrogen here. And so as this comes down, this can kick this out. Probably because this is basic. One thing it could do is that maybe it can take away this proton while this is happening. So you can do it step by step, or you can do it all at one time. It doesn't really matter. Because probably they both happen. And then we'd repeat the same thing on the other side. All right, so let's try a different problem. So I wrote down several problems, and I'm just going to be kind of like scavenging through your textbook. So let us go to chapter 21. So the question is asking you, if you're starting with ethyl acetoacetate, how do you get to this? So ethyl acetoacetate is this thing. And so what we want to do is we notice that we have 1, 2, 3, 4, 5, 6 carbons, and I have this structure. So more than likely, what I would need to do for this reaction is I'm going to have to extend the number of carbons that are on here. And then I also are going to need to make a ketone on here that we're going to have to protect. Now, because I already have a ketone on this structure, there are a couple of different ways that I go about this. So one way that we could go about this is that we can react this with a Gilman to extend this molecule and put a ketone on there. But the problem is we're going to end up with 2 ketones. So I would propose first protecting the ketone that's already on there with this alcohol in catalytic acid to give you this thing. And then we can react this with a Gilman. If you try to do a Grignard to extend it, remember you're going to add multiple carbons. So I want 1, 2, 3, 4. I have 4. I need to add 2 more. So I could use something like ethyl magnesium bromide and with some acid next. And then I can make this thing. Okay, so now I have the long chain. Then I can oxidize this with something like potassium permanganate or PCC or any oxidant really. So I'm going to just put generically oxidant because any oxidant will do this. And then I can use anything like the Wolff-Kishner reaction. With a lot of heat and then end up with this removing this group off of there. So that's one way. There are other ways of doing that, but that's just one way. So in the next one, I have ethyl acetoacetate. Again, I have 1, 2, 3, 4 carbons here. 1, 2, 3, 4. So what I could do is, again, I can protect it, the ketone. So I'm just kind of skipping these steps because we already saw them. I can use something like phenyl. Sorry, here I used a Grignard. I said I want to use a Gilman. So that's this rather. So I would use another Gilman here. Make this thing. And then pretty much the same thing that I did before. I got rid of the carbonyl. I would use something like the Wolff-Kishner. And again, like I said, there are other ways of doing this. I could have done like a decarboxylation by adding more groups, and I'll actually do another example where I could do something like that. And then I could deprotect. And I just need an acid to deprotect. So I'm going to erase what's on here. And I'm going to give you a different way of us doing this. So remember that we can take these structures and we can add more carbons onto it. So here I have 1, 2, 3, and if I wanted to add 3 carbons, I can just use a base. So let's say ethoxide and deprotonate. And then if I use propyl tosylate or propyl bromide or something like that, I can do an SN2 and replace this. All right, and then if I use a strong acid and heat, I can first make this, it becomes initially a carboxylic acid. So this becomes a carboxylic acid and you increase the heat and it undergoes decarboxylation. And then I can do my protecting group. So this is another way, and this is actually an easier way than the one that I did a little bit before. And we could do something very similar to this one right here. And in the end, we can reduce the carbonyl. So something like this. So I'm going to just kind of skip ahead to this part. So you just use a base and then you use something, so 1, 2, 3, like benzyl bromide or something like that, and add that right here. You do the same thing again with the heat and decarboxylation, and you're going to end up with this thing. And then you can just reduce this with sodium borohydride. I'll write that over here. An acid, and you get that product. So that's just another example. And I know I'm just kind of quickly talking you through some of these problems. All right, let me pick one more problem to do. How about let's do 108. So in this problem, we're using an acid catalyst and a secondary amine. And remember, that makes enamines. So when I do this, I just replace the oxygen and put a double bond here. So A would work out to be this thing with our double bond. And then in the presence of, because this is a nucleophile, in the presence of our iodide, we can protonate this thing. All right, so we have our 2 nucleophiles, but remember this is also a Michael donor, and so it's actually sort of electrophilic, nucleophilic right here. We can use this double bond, and actually what it turns out to be able to get this structure, we have our methyl iodide being attacked by our double bond. We end up with this thing. We're going to end up putting a ketone where that nitrogen was, and that methyl picked up the methyl next door to the carbonyl once this thing opens up. So B would be that structure. All right, so let's do another set of problems, and I'll probably do another video after this as well, but not for a grade or anything like that. So we're going to do a problem on the Robinson annulation. So I just wanted to pick one. And in this case, we have this Michael donor, or what can eventually be a Michael donor. We're going to draw, I know it says just draw the product. I'm going to actually draw the mechanism for you as well. And this is the Michael acceptor. And this is where your Michael donor is going to react. So we take our we deprotonate this hydrogen first, make our Michael donor that way. Now we can react this with this alpha beta unsaturated carbonyl, attack right here, open this on, come on, open this up. So I'm going to count my carbons 1, 2, 3, 1, 2, 3, 4, 5, so that I can make sure I draw this correctly. And then I protonate this thing. And then I can tautomerize it. We get our enol, and then this can undergo tautomerization. And then from the bond, that. we would get our ketone. And then since it's a Robinson annulation, the next step is to do the aldol condensation. So I'm going to take one of these hydrogens. Remember, there are 3. I'm just not drawing them all in because we are smart and we know that there are 3 there. So I make my enolate. That can attack one of these carbonyls. Open this up. And it's acting up today. It's a little slow. I'm actually going to draw this on this side. I'm going to continue over here. My pen is a little bit lagging. So I'm just going to continue over here just because I want more space. So this is 1, 2, 3. Carbonyl is on 4. And then 5. I'll draw this a little bit better. So this is carbon number 4. I'm sorry, I'm just doing these kind of on the fly. I don't have the answers in front of me, so you know it's gonna take me. I'm trying to draw these kind of freestyle. So this is 4 and 5, and so I get this ring. I can protonate this. Make our alcohol. And then we can take sorry. This is a 6-member ring. It just looks kind of funky. We can take our base and we can deprotonate and get our aldol condensation product. So our product should end up looking like this. So you want to practice this. I would suggest practicing it also with the enol, the enamine as your enamine also as the Michael donor. That's a good one to also practice. I'm hinting strong, very, very strongly at you by telling you this. All right. Let's try another problem. All right, so I want to do this one. So this is looking at a synthesis. And if we look at the molecule, this part of the molecule kind of looks like what we were given. And then this looks like a double bond that can be formed. And notice it's a carbonyl, it's an alpha beta unsaturated carbonyl. So in my mind, maybe I can do an aldol reaction with this. So if I take this original molecule and I add some sort of base to it, I'm going to deprotonate at this side. So I'm going to say like sodium hydroxide or LEA, for example. And to remember when we did this, we kind of like went forward in terms of figuring out what aldols are. You can figure out how to do that backwards. So if I cut right here and put carbonyls back on this, that's what I would have needed to start with. So a double bond, another double bond, and then the phenyl rings. I could have drawn it like this. And that would be my second step. So using this to do an aldol condensation would be a good way of doing that. All right. In the next reaction, what I can do is I can do, in this one, I have this ring, so it's probably this thing. And notice I have this kind of ketone. My vision for this is that maybe I could do a Michael addition and onto this reaction on this compound, or I may have had something there that I could have done some sort of substitution with on this molecule. Now, what we do know is that these enolates, if I made this in an enolate, it's actually not really a good Michael donor. It more than likely would react to the ketone and do an aldol reaction. But what I can do is take that acetophenone and I can make it into an enamine. So I can take some sort of secondary amine, make this thing into an enamine. And the R could be anything you want. Now, this is a good Michael donor. And if I took this molecule and you may want to practice drawing that mechanism because it might be a good one to draw. So this can essentially react at that position. And after you're done with the Michael addition, you're going to end up with this thing. I'm just kind of drawing it upside down, but it's fine. And then if you hydrolyze this, this goes back to that product that you want. All right, I'm going to clear the screen. I'm going to do the first one. So this more than likely would be like an intramolecular Claisen. That's how we probably close this ring up. And notice that you just have like these extra methyls off of this molecule. So if I were to do a Claisen on this molecule, essentially I can close this ring up like this. And so that would be 1, 2, 3, 4, 5, 6. So a 6-membered ring. And again, it might be helpful to you until you feel comfortable with this to draw the mechanisms. And so this would end up being like that. And then what we can do is we can do a alkylation at this position right here. So if I were to take like methyl iodide and some sort of base, so something like ethoxide, like sodium ethoxide, and then methyl iodide, I'm going to end up with this thing. And then we could use heat and make a little bit of heat. Ooh, I didn't give myself any space. Turn this into a carboxylic acid. So essentially, I'm going to try to get it to do a decarboxylation. And then with high heat, so if I increase the heat, I'm going to get this molecule. And remember, if we want to add a methyl group in the less substituted side, if I use a large base like LDA and follow that up with my alkyl halide, but I want to do LDA at low temperatures, so like negative 78 degrees, it's only going to go on the less substituted side. So that's how I would get this product. All right. So definitely make sure that you're practicing. I'll probably do, like I said, maybe a couple more videos as I get some time. And I won't make them graded videos, but just for you to take a look at them and, for practice.